Welcome. Today we shall be looking into the macroscopic balances, and this is macroscopic balance relates to all the things like mass, for energy, for momentum. So this particular topic will be spread over a few lectures. So this is the first lecture on the macroscopic balances. So in this we shall be covering the conservation law in the integral form and then in the differential form. First let us see that what is the conservation in integral form. So for that we have to first consider a volume specific property for mass, energy or momentum, and that is represented by say phi hat, which is a function of position vector r and time. That is, whenever any kind of property is there, that will change spatially as well as temporally, means with different locations and with different times. So in general, any property will be a function of both position and time, and that position is given by the position vector r and time is given by t. Now please understand, this position vector r can be represented in various manner in various coordinate systems. So whatever notations we are using now, this is independent of the coordinated system. Now again let us understand that what we mean by volume specific property for mass, for energy and for momentum. Here we write in this table the conserved property and the corresponding value of the phi hat. Now here you see that for mass it is the density or concentration. Density when we are talking of the whole mixture, okay, then we talk of density, and concentration when we talk of species by species. Okay. So it can be either density or concentration. Then for momentum it will be density into the velocity. Then for energy it will be density into specific heat into the temperature, that is the energy content or the momentum of a given mass. And understand this, this density is the one which is telling us mass per unit volume. That is how each of these are becoming volume specific properties. Next we come to a particular equation, and this is a very famous equation given by Reynolds, and we call it Reynolds transport theorem. And what is this is like this, that this is the mathematical representation of this particular equation. Here what it gives. Here first, to understand this, let us first look at the control volume V, and this left hand side tells us that how a particular specific property is changing within a volume with time. So here this integral is over the volume, that means because it is volume specific, so when I integrate over the volume I get the total value. Okay, so this total value within the control volume, and how is it changing with time. So and this change, what is happening due to some influx or outflux from the control volume or in the control volume, and due to some kind of generation. So in effect this is this particular term is showing the net influx minus influx and outflux, and this is the generation, and due to this influx, outflux and the generation, what is happening inside the control volume. And now you see that this particular flux is happening at the surface. So we are taking the surface integral, and this F is representing the control surface, and J representing the flow into or out of the control volume crossing the control surface. This is important, the particular flow has to cross the control surface, and this NF is the outward unit normal vector from the control surface. And when we take the dot product, because this is a vector, this is a vector, when we take the dot product of the two vectors, we get the flux, and this last one is this, the source term to account for any generation or consumption of this particular property within the control volume. Okay. Like for example, in case of mass balance or mass conservation, this Q will represent some kind of reaction that might be either consuming the particular species or might be generating the particular species. Okay. So now you look at this, that in this particular integral form, that we are integrating over the whole control volume. So over the whole control volume, this is the whole surface, and this cyclic integral means the surface is bounded. Okay, so there is no gap between the surface. So that's the meaning of the cyclic integral. Okay, and this particular thing again, it is over the volume, because this generation is per unit volume. Now you see, pictorially we can also see that we are drawing this particular control volume, and here we are showing something is coming in and something is going out, and this F is showing the control surface. So now you can see that this is the outgoing normal, and depending on the theta value, that theta means the angle between the normal and the flow stream. Now here you see the theta for the outgoing stream is acute, okay, that is less than 90 degree. However, for the input stream it becomes obtuse, that is more than 90 degree, and when you take the dot product, that is cos theta. Okay, so this into cos theta, you see that this gives us a positive value, whereas this gives us a negative value. So automatically you see that by defining the dot product between the flux and the normal, we are able to account for the influx and outflux. Okay, so it is very important that for you to know how to draw this particular normal, and normal is always outgoing, never make it ingoing. Okay. Now this particular system again we take on a actual system. Now here we have considered a flow through a flow divider. What it means, that a particular flow is coming and then it is getting divided into two streams. So here we find that we have one input and we have two outputs, and again for the input side what we do, again we draw this particular normal, that is outward normal from this surface, and this is the incoming stream. So we can take the dot product between the two, and which we shall get a negative value, whereas for the outgoing streams we find the dot product between this flux and this particular normal will lead to positive values. Okay, so this is how we can see that we are able to implement this particular flux concept. One thing is this, that in this particular control volume we have neglected any kind of reactions, that means any kind of mass generation or consumption. So here we are just showing that how the mass is getting conserved by this particular example. Similar things can be done for the energy and for the momentum transfers also. Now let us go to the conservation equation in differential form. Now when we say differential, what it means is this: we choose a very small control volume, that is we call it infinitesimally small. Now this small is arbitrary again, and this is a relative concept. How small? It will depend on the overall system, and in that overall system what kind of how closely one wants to analyze, that will define the size of the control volume. Anyway, we say that we are choosing a very small control volume, and then when we write this conservation equation we get differential form, and here we apply the Gauss divergence theorem to the surface integral to convert it to a volume integral. So I will not be going into the details of this Gauss divergence theorem, which is covered in some mathematics course. So without going into detail, we simply write the Gauss divergence theorem and put it in this fashion. Now what we find here, that the same integral form of the conservation equation has been reduced to this particular form using the Gauss divergence theorem, and we find that this divergence means here we get the divergence of the vector j, and this divergence is the dot product of the nabla and the particular vector. Now what is nabla? Nabla again is defined differently in different coordinate system. It basically gives us the three-dimensional change of a given vector. Okay, so here we have written for Cartesian coordinate, this nabla dot j will look like this. For the cylindrical coordinate, it will look like this, and for the spherical coordinate, it will look like this. So depending on the coordinate system, this delta dot j will change its form, and in my previous lecture I have also given you the relationships between the various coordinate systems. Now, in this particular conservation law, what we encountered these flow or transport terms. So, let us see what it means. Now, total flow can be divided into two components. One component is the convective flow, and is the diffusive flow. Now, the convective flow is given by Jc and diffusive by Jd. Now, this convective flow means which is happening due to the motion of the particular fluid, okay, or the particular material, and the motion is given by some velocity field v. So, this Jc is given by the particular property, okay, and the particular velocity field. So, when we take these two products, we get the convective flow. Okay. Now, in this particular equation, we obtain the value of the velocity field by solving the momentum balance equation. So, you can see that if we are looking at the mass balance, momentum balance automatically creeps in and they become coupled. On the other hand, when we talk of the diffusive flow, it depends on the gradient of the potential, some potential. Now, in simple terms, it means that the diffusive flow will be happening whenever there is some kind of gradient. For example, if you look at heat transfer, it will occur only when there is a temperature gradient. That means the temperature will be representing this value. Okay? And similarly, whenever there is a mass transfer, like for example, you are trying to dissolve sugar in water or milk. Now, what happens? Because there is initially there is a gradient of concentration, so you find that sugar is going inside the liquid. Okay? So, in that case, the concentration will be this value. Okay? So, that is what it means, that diffusive flow occurs due to gradient of the potential, and this is given by this particular thing, that negative of d into this, again this nabla and into this scalar. Understand this? This is a scalar field now. This scalar field is now being converted to a vector field. Okay? Now, this d in general is a diffusive coefficient. It can be mass diffusivity, it could be momentum diffusivity, it could be thermal diffusivity, okay, depending on which kind of conservation property we are applying. So, here we are putting d as an arbitrary parameter. Okay. And as I mentioned that this sign may represent some mass balance, it will differ for mass balance, for momentum balance and for energy balance. Next we come to source term. Now, what is this source term? This will be something which is other than the diffusive term or the convective term. Anything other than that will be the source term. Now, why this source term comes? It can come due to various factors. One factor is the chemical reactions. Now, I have shown you some chemical reactions which are important for us. For example, here you see that how the methane is getting combusted to generate some energy, and in that it is giving us carbon dioxide and water. And this methane is we are getting it from the CNG, that is the compressed natural gas, or LNG, that is the liquefied natural gas. So, this is a very common thing which we are using to get energy, that is this methane is a fuel. Okay? And this another example that how the water can be disintegrated by electrolysis to give us hydrogen and oxygen. So, here this is another kind of reaction. So, this can be this kind of simple reaction in terms of the molecules involved, not in terms of the conditions, of course. Another kind can be quite complex reaction can be there, that in this we see that there are some complex molecules, and to get another product from this molecule we have to follow several steps with several temperature conditions and several kinds of reagents to obtain the final product. So, reactions can be of various types, but they all lead to some kind of source term. Another source term can be due to energy dissipation or conversion, and this can be due to heating, due to noise or friction, and it could be from compression or density changes within the system. Now, here I have shown an example that how energy can get dissipated whenever we are riding, say, a car, we are burning some fuel like diesel or petrol. Now, what happens that whatever after combustion of this diesel or petrol, whatever energy is coming out, all the energy is not used up to drive the car. We find that there will be some heating up in the system and will be quite noises. So all these are the sources of energy dissipation in the system, and you will find that out of the whole energy of combustion generated, only a part will be used up for this kinetic, that is the useful energy. Okay, so but this is also all these energies will be part of the source terms. Next we come to some other source terms due to the pressure field. For example, a turbine. In the turbine, you know that we put some kind of pressurized gas and the turbine propeller rotates, and that is how we are able to convert that pressure energy into some useful energy. Then we have a gravitational field. In the gravitational field, we have the aircraft, space vehicles, which have to be designed so that they can overcome the gravity and move. And then we have electrical field and magnetic field, which generally come together. We call them electromagnetic forces, and here I have shown you some day-to-day devices which depend on the electromagnetic forces, and you find that these things come because there is some kind of a magnet in the system, and there can be some coil which if you are passing some electric through the coil, it will be generating some magnetic field, or vice versa. So these are some devices we have found. See, and you see also, for example, whenever you are running a motor, you find that on running for a long time, the motor gets heated up. This heating is nothing but the dissipation of energy. Okay, so all these things are the source terms. Now these source terms depend on the potential again, corresponding to equivalent extensive property characterizing the process system. For example, we have concentration, temperature, etc. They are the, as I told you earlier, this will be depending on that what kind of dissipation we are having, whether we have mass dissipation, whether we have energy dissipation. Depending on that, it will be, this value will be having different connotations. Now, after learning about this integral differential operator, now what we do, we go to the differential form of the conservation equation in a operator way. Operator means now we introduce the Nabla operator to you. Now what we shall see, that we are just putting the values of j here, and we are rewriting the same equation as I wrote earlier. So here I am writing that minus Nabla of jc plus jd for j, and now we are taking them out. So first we find that this jd we are putting as minus d, this Nabla into psi rt, and this negative gets cancelled, it becomes positive, and this becomes this jc we are putting this value. So it is retaining the negative value and plus this. Now in this particular equation is coordinate independent. It does not depend which coordinate, that is, this is a general statement without any dependency on the coordinate, and this equation now can be modified as per the case. For example, if the diffusivity is constant, it is not changing, then we can take it out of this particular Nabla operator, and then this becomes delta square, Nabla square, this psi rt. Now Nabla square means, so in say example, in the rectangular coordinate, this Nabla square will be del square by del x square plus del square by del y square plus del square by del z square. So this kind of simplification can be done from case by case basis, and sometimes if we find that the diffusive contribution is less than the convective contribution, then we can drop this particular term, and vice versa, if we find for some system the convective term is less dominant than diffusive term, then we can also neglect this. And in some systems, we can also drop this term out if there is no generation or consumption. Now, this system is generally non-linear because this q and d are not constant, and many times we find that these equations are coupled. That means, as I showed you earlier, the momentum equation and the mass balance may be coupled. The mass balance may be coupled with the energy balance equation, because if in the mass balance we have the densities, and the densities are functions of the temperature, and temperature can be obtained from the energy balance equation, and the energy balance equation also we are having the densities, specifics, etc. So in that we find that everything becomes a coupled set of equations. So we can get in general non-linear coupled differential equations. Now, this reaction term is the one which many times for the source term reaction term can give rise to this coupling, and this reaction depends on the concentration which can be obtained from the mass intensive property, and this is temperature, that is the energy intensive property, that is we are obtaining them either from the mass balance and from the energy balance equations. Now, we come to another important concept, that is the lumped parameter system. In this lumped parameter system, it may be steady or unsteady, and it is basically a scalar field of intensive properties that is a function of only time. That means there is no dependence on the location. And because there is no dependence on location, we find from the previous equation that the Nabla operator will not be coming into picture. So, only we have the left hand side in which we have the time derivative. So, it leads to a ordinary differential equation. Example is this: when we mixing up a sugar in milk to bring the whole system at a same concentration, that is it becomes an homogeneous mixture. What it means that there is no concentration gradient, that is we can see that there will not be any variation of sweetness of the milk at different locations. And then on the energy side, if we are mixing a hot and cold liquid, what we find that ultimately they will bring to some uniform temperature. Okay, that is also means that we are avoiding any kind of locational variation of the particular property, that is the temperature. And in these cases, we apply the integral form of the conservation law, and when we do so, we find that the flux become equal to Jc, because the diffusive term is gone, because there is no gradient. So, the total flux is purely depends on the convective flux. Now, coming to the control volumes, because whenever we are making such kind of balances, we need to select a control volume. So, what is control volume? A control volume represents some elementary region which will be representative of the whole system, and in this we see that we can write the conservation law, okay, with the appropriate assumptions. So, these control volumes are also known as balance volumes, because over the control volume we are applying some kind of balance equation for the conservation. So, when there is some spatial variation of the conserved property, then we have distributed parameter system, and for this kind of system there will be representative balance volumes are defined, in which the conserved property is to be taken uniform. That means we have a bigger control volume, but when we find in a bigger control volume we have distribution of property, then we make smaller control volume within the bigger control volume, and in each of these smaller control volumes all the properties are taken to be uniform, even though in the overall there will be distribution, but in the differential control volume there will not be any distribution of the property. And different control volumes, like for mass, energy and momentum, and this one energy balance may be having more than one mass balance. That means it is not necessary that the number of control volumes for mass balance is same as that for the energy balance. So, these number of control volumes may differ, and I will show you by example that how we find that energy balance and mass balance control volumes may not count the same. And these control volume concepts form the basis for the modeling any system. Now, let us see typical types of control volume. One can be that if you are talking of fluids, it can be single or pseudo phase. Single means there is only vapor or liquid or solid, or pseudo phase. That means suppose we have some kind of emulsion where we have two immiscible liquids, then we, for simplicity's sake, what we can do, we can assume an overall phase, and we call it pseudo phase, which will be having some properties of some average properties of the two constituting phases. Then we can have perfectly mixed phase, like in case of gaseous mixture, or we can have uniform or homogeneous flow pattern, okay, where there is no locational gradient. Now, for selection of control volume, this is very important, how we select. Now, selection is arbitrary, but depending on the selection we make, our analysis may get simplified or may get complex. So, with experience it comes to us also that how to select a control volume before we start writing the balance equations. And only thing is this, a control volume should ensure accounting for all the inflow and outflow of the conserved properties. That means, if there is a energy balance to be made, we have to make sure that the control volume is made in such a manner that it cuts the surfaces in a way that we can take into account all the incoming energy and all the outgoing energy. If this control volume does not do that, then we will not be able to make the proper balances. So, it is that is what it says, that a control volume must ensure that it can take into account all the inflows and outflows. May be fixed or moving, may be rigid or flexible, and here in this particular figure I have shown you the meaning of this. Now, you see there is a from the nozzle some fluid is coming out and this nozzle is not moving. So, we call it a fixed control volume. Similarly, here we have a helicopter. Now, when this helicopter fan is moving, we find that the air is getting also rotated, and in this case we find that this is because of this propulsion, this helicopter is moving forward. Okay? So, if we take this as the control volume, we find that this is the helicopter is moving, so we call it a moving control volume. On the other hand, if I look at a balloon, now what was happening, that whenever you are inflating or deflating a balloon, for example, you can also do the same thing with a football or a tube of the cycle. So, whenever you are putting some kind of air, you find it inflates. That means the volume is changing. So, we call this a deforming control volume. Okay? Whereas in case of say pump, when through a pump some fluid is flowing, but the pump structure is not changing, it is remaining same. So, it is a rigid control volume. So, depending on the different types of the processes, we may have these variations, and we can have combinations, like we can have fixed and rigid control volume, we can have fixed and flexible control volume, we can have moving rigid control volume and moving flexible control volume. So, all these kind of combinations are possible whenever you are selecting the control volumes. And here, as I was telling you, this is an example of an evaporator where we find that energy balance and mass balance control volumes may be different. So, in the first figure what we see, that we are taking the control volume as the overall evaporator, and this evaporator, some feed is coming, and feed is liquid generally, and this is being heated up with some steam, and due to which the liquid is converting to vapor. We are taking the vapor out from the top, liquid from the bottom, and here we can make a mass balance, energy balance over the whole evaporator. If we do that, we will be obtaining that how the total mass inside the evaporator is changing, or how much energy is getting accumulated in the evaporator. On the other hand, if we want to know that how the liquid level is changing due to evaporation, that cannot be known if we choose this particular control volume. In that case, we have to choose two control volumes, one will be for the vapor phase, another will be for the liquid phase. Now, in this way, we shall be able to determine the change in the liquid level due to the evaporation. Okay? But at the same time, if we want to still know the energy in the system, how much energy is accumulated, then we need not choose these two volumes separately, because the total energy is the summation of the energies of the two phases. So, for the energy balance, we can still go with the previous control volume, that is the total evaporator. So, you can see that in this case, the energy balance control volume is having the two mass volumes within it. So, in that way we conclude that it is not necessary that the number of control volumes for the mass and the energy must be the same. Now, whenever see mass lumped parameter, we mean that there will be homogeneity of the states within that control volume for global description of the system, and the scalar field is lumped into some representative value. That means we are attributing only one value of the intensive variable, whether temperature, pressure, concentration, etc. within the control volume, and this lumping is coming only when there is a system is well mixed. Okay, and that is why they are called well mixed system. This mixing brings the whole system at a given state. Okay, and this is applied for various cases like process design, process safety. Then if I want to start up or shut down a particular process, and for process control and diagnostic. For all these systems, we do not need to know the spatial variation of the properties. Their overall behavior, that is inlet and outlet behavior, is good enough. So we go for the lumped parameter systems. Thank you.